Welcome to the General Chemistry 2 class. This section is on acid-base equilibria and salt equilibria. This lesson is about buffer solutions. Let's begin. In this lesson, we will describe how a buffer solution maintains its pH. A buffer solution, or simply buffer, is a solution that resists drastic or sudden change in pH upon addition of small amounts of a strong acid or a strong base. It consists of a weak acid and its conjugate base or a weak base and its conjugate acid. Example number 1. Determine whether the following pairs of compounds can form a buffer in water. Solution: A. Hydrochloric acid is a strong acid. Sodium chloride is a source of chloride ion, the conjugate base of hydrochloric acid. As a base, chloride ion is so weak that it cannot accept a proton in solution. Thus, this pair of compounds cannot form a buffer. B. Sodium dihydrogen phosphate is a source of dihydrogen phosphate ion, while sodium hydrogen phosphate is a source of hydrogen phosphate ion. Dihydrogen phosphate is a weak acid, while hydrogen phosphate is its conjugate base. Thus, the mixture of these compounds can form a buffer. C. Ammonia is a weak base. Ammonium chloride, when dissolved in water, produces ammonium ion, which is the conjugate acid of ammonia. Therefore, the two compounds can form a buffer. So, how does a buffer works? A buffer consists of substances that react with the added strong acid or strong base. So, how does a buffer works? A buffer consists of substances that react with the added strong acid or strong base. The graphs below show how pH changes when an increasing amount of a strong acid, which we see on the left, or a strong base, we see on the right, is added to a buffer with a pH of 7 and pure water, whose pH is also 7. In these graphs, notice that the pH of the buffer does not change significantly with increasing amount of strong acid or strong base, while the pH of water changes drastically in the presence of the strong acid or strong base. Consider a buffer consisting of acetic acid and sodium acetate. The governing equation is the ionization of acetic acid in water, which is a reaction of equilibrium. Upon addition of small amounts of a strong acid like hydrochloric acid, the basic component, sodium acetate, is the one that reacts with it. The hydrogen ion from hydrochloric acid is taken up by acetate ion to produce acetic acid. This process results in a slight decrease in the concentration of acetate ion and slight increase in the concentration of acetic acid in the buffer. Upon addition of small amounts of a strong base like sodium hydroxide, the acidic component, acetic acid, is the one that reacts with it. Acetic acid gives off its proton to hydroxide ion from sodium hydroxide to produce acetate ion and water. This process results in a slight increase in the concentration of acetate ion and slight decrease in the concentration of acetic acid in the buffer. To summarize, for a buffer whose acidic component is Ha and its conjugate base is A negative, The following diagram shows how buffer reacts with an added strong acid or strong base. The hydrogen ion concentration can be calculated from the given Ka of the acid and the new concentrations Ha and A negative. Consequently, the pH of the buffer upon addition of a strong acid or strong base can be calculated from the hydrogen ion concentration. So example number 2. Calculate the pH of the solution consisting of 0.50 molar acetic acid and 0.50 molar sodium acetate. The Ka of acetic acid is 1.75 times 10 raised to negative 5. So solution. We need to determine the equilibrium concentration of hydrogen ion in the solution. Let us construct a table showing the concentration before and at equilibrium. Initially, only 0.50 molar acetic acid and 0.5 molar acetate ion are present. No hydrogen ion is present, so the equilibrium shifts to the right. This means, as equilibrium is achieved, acetic acid concentration is reduced by X, while hydrogen ion and acetate ion concentrations are increased by X. Thus, at equilibrium, the concentration, which is in molar, of acetic acid is 0.50 minus X. That of hydrogen ion is X, and that of acetate ion is 0.50 plus X. Use the Ka expression to solve for hydrogen ion concentration. Ka is hydrogen ion concentration times Ka is equals to hydrogen ion concentration times acetate ion concentration divided by acetic acid concentration. Plugging in the Ka value and concentrations, we have 1.75 times 10 raised to negative 5 equals X times the quantity 0.50 plus X all over the quantity 0.50 minus X. Assuming X is too small, we can neglect X that is added to or subtracted from the initial concentration. So, solving for X, we obtain 1.75 times 10 raised to negative 5 molar. Only the underlined digits are significant based on the given initial concentrations, which have two significant figures since the value of X passes the 5% rule. Our approximation is therefore valid. The value of X is the hydrogen ion concentration. So, to get the pH, take the negative logarithm of the hydrogen ion concentration. This gives us a value of 4.76. Example number 3. Let's investigate quantitatively how pH of buffers changes in the presence of small amounts of an acid or a base. So, example number 3, let us calculate the change in pH when 1 liter of the buffer in example 2 is mixed with 0.050 moles of nitric acid. Assume no change in volume occurs upon addition of the acid. So, solution. Nitric acid is a strong acid and it ionizes completely in water to produce hydrogen and nitrate ions. Given that 0.050 moles of nitric acid is mixed in the buffer, the same amount of hydrogen ion is released. The concentration of hydrogen ion is calculated by dividing the number of moles, 0.050 moles, by the volume of the buffer, 1 liter. The answer is 0.050 molar. Next, determine the concentrations of acetate ion and acetic acid upon addition of the strong acid. So, as acetate takes up hydrogen ion from nitric acid, its concentration is decreased by 0.050 molar. So, its concentration becomes 0.45 molar. On the other hand, the concentration of acetic acid increases by 0.050 molar. So its concentration is now 0.55 molar. Now, we will use the new concentrations of acetic acid and acetate ion to calculate for the hydrogen ion concentration. As equilibrium is reached, acetic acid concentration is reduced by X, while the concentrations of hydrogen and acetate ions is increased by X. At equilibrium, the concentration in molar of acetic acid is 0.55 minus X, that of hydrogen ion is X, and that of acetate ion is 0.45 plus X. Now, substitute the obtained equilibrium concentrations into the Ka expression for acetic acid. Again, we will assume that X is too small that we can neglect X that is added or subtracted from the initial concentrations. Solving for X gives us 2.13 times 10 raised to negative 5 molar. Only the underlined digits are significant. Based on the initial concentrations, which have two significant figures, the value of X passes the 5% rule, so our assumption is therefore valid. The value of X is the value of the hydrogen ion concentration. Now let us calculate the pH of the solution by taking the negative logarithm of the hydrogen ion concentration. Doing this gives us pH equals to 4.67. So to calculate the change in pH upon addition of nitric acid, subtract the pH before addition of the acid, or the pH we got in example number 2. From the pH of the buffer upon addition of the acid, 4.67 minus 4.76 is equals to negative 0.09 pH units. The answer implies that the presence of nitric acid lowers the pH of the buffer by 0.09 units, which is insignificant. In example number 3, we calculate that the change in pH when 1 liter of the buffer in example number 2 is mixed up with 0.020 moles of sodium hydroxide, and we assume that no change in volume occurs upon addition of the base. Importance of buffers. Buffers are important in keeping the pH of chemical and biological systems essentially constant. For instance, buffers should maintain the pH of various body fluids in order to regulate physiological processes. So, to summarize, a buffer solution or a buffer is a solution that does not significantly change in pH upon addition of small amounts of a strong acid or a strong base. For an aqueous solution to be a buffer, it must be composed of a weak acid and its conjugate base, or a weak base and its conjugate acid. Thank you for listening, and that would be all. Now, let us proceed to the exercises. Let us proceed to the quiz for buffer solutions. Part 8. Number 1. Which of the following is not true about buffers? Letter A. A buffer consists of a weak acid and a strong acid. Or is it letter B? A buffer resists drastic changes in pH upon addition of small amounts of an acid or a base. And letter C, a buffer can be prepared from a weak base and its conjugate acid. Or letter D, A, B, and C. Number 2. Determine whether the following solution is a buffer. So, HNO3 and NaNO3. So, is it A buffer, or B, not a buffer? Number 3. Determine whether the following solution is a buffer. HCOOH and HCOO and A. Is it letter A or letter B? Select the correct answer. Number 4. Determine whether the following solution is a buffer. NaOH and hydrochloric acid. Is it A buffer, or B, not a buffer? So let us proceed to number 5. Consider the buffer made by mixing solutions of NH3 and NH4 and O3. So the question is, KOH is added in the buffer. Which buffer component will consume it? Is it A, the NH3, B, NH4 plus, or C, NO3 negative? Number 6. Consider the buffer made by mixing solutions of NH3 and NH4 and O3. The question is, HClO4 is added in the buffer. Which buffer component will consume it? Is it A, the NH3, B, NH4 plus, or C, NO3 negative? Next is the number 7. So, consider a buffer consisting of H2PO4 negative and HPO42 negative. So, the question is, what is the correct equation showing how buffer consumes an added acid like HNO3? So, is it letter A, letter B, letter C, or letter D? Select the correct equation. Number 8. Consider a buffer consisting of H2PO4 negative and HPO42 negative. So the question is, what is the correct equation showing how buffer consumes an added base like LiOH? Is it letter A, letter B, letter C, or is it letter D? Number 9. Consider a buffer made up of 0.10 molar H2PO4 negative and 0.32 molar HPO42 negative. The Ka of H2PO4 negative is 6.2 times 10 raised to negative 8. So, what is the pH of the buffer? Is it letter A, 7.50, letter B, 8.45, letter C, 6.70, or is it letter D, which is 7.71? Lastly, number 10. Consider a buffer made up of 0.10 molar H2PO4 negative and 0.32 molar HPO42 negative. The Ka of H2PO4 is 6.2 times 10 raised to negative 8. So, what is the resulting pH when 1 liter of the buffer is mixed with 0.01 mole HClO4? Assume no change in volume occurs upon addition of the acid. So, is it letter A, which is 8.54, Letter B, 6.90. Letter C, 7.66. Or is it letter D, 8.43? And that would be all for the quiz of part 8, which is U buffer solutions. So I hope that you have learned something, apply it, and always remember to be like your protein, stay positive.